Sveiki Vilnius! But wait, there's more. Aš esu Dave Aronson, T-Rexas iš Kodosaurus, ir atskridau čia ant savo augintinio pterodaktilio, kad išmokinčiau jūs, kaip reikia naikinti mutantus. Visgi, to jau esu pasakojama angliškai. Mainly because you just heard almost all the Lithuanian I speak. And for those of you who think I look a little familiar, you might have seen me on stage last night. Right there behind Dylan. That's probably the only way a singing voice like mine is going to be on stage with the line breakers. And just a bit ago, he mentioned Guy Royce. Yeah, that's him up there. I don't think this laser pointer is showing up very well. Oh well, but to get finally to the topic of the talk, what on infinite Earths makes mutation testing different from all the other software testing techniques we know? The big difference is that most of the others are about checking whether or not our software is correct. But mutation testing assumes that our software is correct, at least in the sense of passing its tests. Instead, mutation testing is looking at two other properties, and in a typical code base, I think the more important one is that our our test suite is strict. Now you might be thinking, isn't that what test coverage is for? If we have 100% coverage, doesn't that mean that our code is fully tested? No. The only thing that test coverage tells us is that at least one test ran the code that it claims is covered, what usually shows up in green. And conversely, that none ran the rest of it, which usually shows up in red. It tells us nothing about whether the correctness of any particular chunk of code had anything to do with whether any test, let alone any specific test, passed or failed. And isn't that what we really mean when we ask if a piece of code is tested? I think it is. So how can we tell if a piece of code really did get tested? As you may have guessed, that's where mutation testing comes in. To check whether our test suite is strict, a mutation testing tool will try to find the gaps that let our code get away with unintended behavior. And when we find these gaps, we can fill them in by either adding more tests or by expanding some existing tests. Lack of strictness is usually caused by lack of tests, of course, or poorly written tests. The other thing that mutation testing checks for is that our code is what I call meaningful, so that any tiny little semantic change, as opposed to structural or syntactic, has a noticeable effect on the behavior of the code. Lack of this meaning or meaningfulness, if you're not into the whole brevity thing, comes from code being unreachable or redundant or otherwise just not having any real effect. And when we find such code, we can study it and figure out why it's meaningless and maybe fix it if that fits our intent. But the usual remedy is to just get rid of it. Mutation testing puts these two together by checking that every tiny little change that the tool knows how to do does have a noticeable effect on the behavior of the code, and that our code base is strict enough that at least one test, doesn't have to be all of them, but at least one test will notice that change and fail. Now that's the upside, but of course there are some drawbacks. As Fred Brooks told us back in 1986, there's no silver bullet. Well, maybe that one. Besides, silver bullets are for taking care of werewolves, not mutants. The first drawback is that it's rather hard labor on the CPU, and therefore usually rather slow. We certainly won't want to mutation test our entire code base every time we save a file. maybe over a lunch break or something for a smallish system, or a weekend for a large one. But fortunately, most of the tools include ways to tell it, I just want to mutation test this function, maybe this class, this file, this directory, whatever. And many of them also include an incremental mode. So you can say, only mutation test what has changed since the last time we ran this tool, or the last git commit, or the difference from the main branch. With those sorts of filterings, we can maybe test just the relevant changes every time we save a file, or at the very least, test it over a much shorter break than otherwise. Oh, forgot to change slides for the incremental mode. Anyway, another drawback is that it's often not at all clear what to do about the results. Mutation testing tells us that some particular change to the code made no change in the test results. But what does that even mean? It takes a lot of interpretation to figure out what a surviving mutant is trying to tell us. Their accent is very strange, and they're almost as incoherent as zombies, but with much larger vocabulary, so they're not always on about brains. They're usually trying to tell us that our code is meaningless or our tests are lax, or both. But it can be very difficult to figure out exactly how. Even worse, sometimes it's a false alarm, because a mutant might not make any tests fail, but that's often because it didn't really make a difference in the behavior in the first place. And it can still take quite a lot of time and effort to figure that out. And even if a mutation does make a difference, most programs contain quite a lot of code that we just shouldn't bother to test, like debugging traces. If your correct operation of your program depends on exactly what's in some debugging traces, I think you've got other problems. Fortunately, most of the tools have ways to tell it, don't bother mutating this line, or again, this function, this class, this file, whatever. That's usually done with comments, which can clutter up the code and make it a little less readable. Not a big deal. Now that we've seen some of the pros and cons, how does mutation testing work, unlike this guy? It mutates copies of our code, hence the name. And it does this in order to create test failures, otherwise known as faults. So mutation testing can be categorized as a fault-based testing technique, and this means it's related to something you might already be familiar with, Chaos Monkey from Netflix. Just like Chaos Monkey helps Netflix discover flaws in their error recovery system by using faults, mutation testing uses faults to help discover certain kinds of flaws in our test suite and in our code. But the way mutation testing does this is kind of upside down from what Chaos Monkey does. Chaos Monkey is best known for injecting faults into Netflix's production network. If all still goes well, in the sense that Netflix's customers don't notice and their metrics still look good, then Netflix knows that their error recovery is working fine. Mutation testing, however, injects semantic changes, not necessarily problems. We hope that each of these changes will cause some sort of test failure, but that's up to the test suite. It injects them into copies of our code, not our actual network. And it does its work in our test environment, not production. Whew. And if everything still goes well, in the sense that our tests all still pass, that doesn't mean that all is well. That means there is a problem. Remember, every semantic change should make at least one test fail. But enough about differences. What does it actually do? Let's start with a high-level view. First, our chosen tool breaks our code apart into pieces to test. Usually these will be our functions, or methods if you're using object-oriented programming, but I'm just going to say functions. Then, for each function, it tries to find the tests that cover that function. If it can't find any, it depends what tool you're using. Some of them will warn you and say, hey, we're going to skip this one because we can't find any tests, and you should go add some, or otherwise bring it to the attention of the tool. We'll cover that a bit later. Some of the others will use the entire test suite, which is, of course, horrendously inefficient. So make sure your tests are properly aligned. Anyway, after it finds the tests for a given function, then it makes the mutants from the function. And to do that, it looks closely at the function to see how it can be changed. And for each tiny little way it can see to change the function, it makes one mutant with that one change. In other words, that mutation. And once the tool is done making all the mutants it can from that function, then it iterates over the list, and now we get to the heart of the concept. This chart represents the progress of our tool. They don't generally give us anywhere near all this information, let alone so nicely organized, but it's a conceptual model I use to help illustrate the point. For each mutant derived from a given function, the tool runs the function's tests, but it runs them against the current mutant instead of the original function. If any test fails, this is called killing the mutant, and it's a good thing. It means that our code is meaningful enough that the tiny little change that the tool made in order to create this particular mutant did indeed make a noticeable difference in the code's behavior, and our test suite is strict enough that at least one test did indeed notice that change and failed. Then the tool will mark that mutant killed, stop running any more tests against it, and move on to the next one. Once a mutant has made one test fail, we don't care how many more it might make fail, like maybe some of those blank cells up there. There we go. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the tests pass, then it is said to have survived. And that means that the mutant has the superpower of mimicry, skilled enough to fool our tests. That usually means that our code is meaningless or our tests are lax, and now it's up to us to figure out exactly how. Now let's peel back one layer of the onion and look at some of the technical details of how this works. First, our tool parses our code, usually into an abstract syntax tree. Some tools, especially the ones that are just little experiments, run on alternate things like bytecode or even raw source code, but the vast majority of the ones that are actually ready for industrial use work on an AST, so let's roll with that. So this code, which you don't really have to remember, becomes this AST, which you also don't have to really remember. Just note that there's at least one fully fleshed out function there, as opposed to the few others where I've just said, okay, we've got a function there, never mind what's behind it. Then it traverses that tree, looking for subtrees or branches, if you will, that represent our functions. And after finding them, it treats them like I said before, starting with looking for each one's tests. Ooh. Something's gone wonky there. Okay, there we go. So how does it find the tests? That usually relies mostly on us developers either annotating our tests or following some kind of naming convention, as that kind of way that you might need to bring existing tests to the tool's attention. But these manual techniques are often supplemented and sometimes even completely replaced by the tool looking at what tests call what functions. That can get sometimes a little tricky and unreliable, especially if you're using a test helper function, so the tests aren't calling your functions directly. But it still helps a bit. Now, to make the mutants from the AST subtree that represents one function, it traverses that little subtree just like it did to the whole thing, except now, instead of looking for even smaller subtrees to extract, like a twig or something, it's looking for nodes where it can change something. And each time it finds one of those, it'll make a fresh copy of the whole AST subtree for that function with just that one node changed in that one way. For instance, suppose our tool has started traversing that fleshed out function subtree that I showed you earlier and has gotten down to this if condition. For each way the tool knows how to change that node, it would make a fresh copy of that whole subtree with just that one node changed in that one particular way. And after it's done making as many mutants as it can by changing that node, it'll continue traversing the tree, going on to the next node, and do likewise there, and so on until it has traversed the entire function subtree. Now, I've been talking a lot about changing things, so what kind of changes are we talking about? There are quite a lot. It could change a mathematical, logical, or bitwise, or whatever else you have, operator from one to another. In cases where the language allows it, we can even change from one category to another. For instance, in many languages, we can treat anything as Booleans, and we can treat any kind of integers as bit fields. So if you have two integers, x and y, x times y might become x and y, or x bitwise exclusive or y. When the order of operands matters, it can swap them, like with subtraction, division, exponentiation, and string concatenation. It could change a comparison of order or equality or inequality from one to another. It could insert or remove a mathematical, logical, or bitwise negation. It could remove an entire expression or statement. It can remove a branching condition so that something that might be either done or skipped around is always done. Taking that a step further, it can remove a looping condition so that something that might be skipped around, done once, or done several times is done exactly once. It can change a value from to some other value, such as changing 42 to any of those and many more, but I had to stop somewhere. It could even change it to something of a completely different and possibly incompatible type, like changing a number to a, if I may quote Smeagol, string or nothing. There are many more types of changes, but I trust you get the idea. From here on, there are no more low-level details I want to add, so let's finally walk through some examples. We'll start with an easy one. Suppose we have a function like this. Never mind why, it just makes a good, easy example. Now think about what a mutant made from a function like that might return, because that's what our test would probably be looking at. It sure doesn't look to me like it would have any side effects unless those operators are seriously overridden. Mainly, such a mutant could return results such as any of these expressions or constants, and again, many more, but I had to stop somewhere. Now, suppose we had only one test, like so. This is a rather poor test, and I think at least one reason why is immediately obvious to most of us. But even so, most of these mutants would get killed by this Most of these mutants would get killed by this test, the ones shown here in crossed out green. The ones returning any constant are very unlikely to match. There's no particular reason that the tool would put a 4 there as opposed to 1, 0, -1, plus or minus minimum and maximum integers and floats and infinity and other significant numbers, like maybe 42. Subtracting one argument from the other instead of the exponentiation would get us 0. Dividing them would get us 1. Returning either one alone would get us 2. And at least raising a deliberate error or returning something of a different type should make our test not pass. But addition, multiplication, and exponentiation in the reverse order will all get us the right answer. So mutants based on those mutations will survive our current test. Now, how do we see this happening? When we run our tool, we should get a report roughly like this. The format will vary enormously depending exactly what tool we're running, but semantically, the information should be roughly the same. And that is that if we change the function called power, which is at line 42 of file demo.py, in any of 4 different ways, then all its tests will still pass. And then it goes on to tell us that those 4 ways are to change the function declaration to swap its arguments, to change the function body to change the exponentiation into addition or multiplication, or to change the function body to swap the operands of the exponentiation. So what is this set of surviving mutants trying to tell us? We can tell from a glance at the code that it's probably not trying to tell us about redundant or unreachable code. The body's just one line, so that sort of problem is extremely unlikely. So it's probably a test gap. The question now boils down to, how are these mutants surviving? The usual answer is that they return the same value as the original function, or they have the same side effect, whatever our tests are looking at. To determine how that happens, it helps to take a closer look at one mutant and a test that it passes. So let's start with the plus mutant. Looking at that change together with our test makes it pretty clear that this one survives because 2 plus 2 equals 2 to the 2, to 2, to 2, to 2, 2. And so does 2 times 2, but he's in the background. We can save him for later. So, how can we kill this mutant? In other words, make at least one test fail when run against the mutant that would pass when run against the original code. What we need to do is to make at least one test use inputs to our function such that x plus y is different from x to the y. For instance, we could add a test or change our existing test to something like asserting that 2 to the 4th is 16. A pretty simple concept. All the mutants that our original test killed, this would still kill. But in addition, 2 plus 4 is 6, not 16. So this kills the plus mutant. You see how that works? Yeah, I'm seeing some nods out there. Good. And if you don't see, well, there'll be time for questions after. Better yet, though, 2 times 4 is 8, which is also not 16. We developers should certainly know our powers of 2, at least that well. So this kills the times mutant as well. You will often find that killing one mutant on purpose has a lot of collateral damage among the other mutants of the same function. But the pair of argument-swapping mutants still survive. Wait, how can that be? It's because 2 to the 4th and 4 squared are the same thing. They're 16, both of them. But that's not a big deal. We can attack them separately. No need to kill all the mutants in one swell swoop and be some kind of superhero about it. Again, we can add another test or adjust our existing tests to maybe something like this, that 2 to the 3rd power is 8. 3 squared is 9, not 8. So this kills the argument-swapping mutants. Better yet, 2 plus 3 is 5, 2 times 3 is 6, and both of those are, guess what? Not 8. So the plus and times mutants stay dead, and we don't get any zombie mutants wandering around, even if this were still our one and only test. With these inputs, the correct operation is the only common simple one that gets us the right answer. This isn't the only solution, though. Even if we stuck to single digits, there are lots of ways to skin that flurkin. Now, this may make mutation testing sound simple, but this was a downright, there we go, simple. But this was a downright trivial example. So let's look at a more complex one. Suppose we have a function to send a message, like so. This function, send message, uses send bytes to send as many bytes as send bytes could send, kind of like a woodchuck, looping over and over to pick up where it left off until the message is all sent, a very common pattern in communication and similar software. A mutation testing tool could make lots and lots of mutants from this, but one of particular interest would be this, an example of removing a looping control. That would make our code read effectively like this. Now, suppose that this mutant does indeed survive our test suite, which consists mainly of this. There's a little bit more that I'm not going to show you quite yet, dealing with setting the size and then actually creating the message. But even without seeing that, what does the survival of the non-looping mutant tell us? If a mutant that only goes through this loop once acts the same as our normal code as far as our tests can tell, then our tests are only making our normal code go through that loop once. Okay, so what does that mean? You'll find that figuring out what mutants are trying to tell you often involves a lot of asking yourself, okay, so what does that mean? Often deeply recursively. But in this case, it means we're not testing sending a message larger than send bytes can handle in one chunk. Now, there are lots of ways that could happen, but we're only going to look at two right now. The most likely is that we really should have, but forgot, or just didn't bother to test with a message larger than our chunk size. For instance, suppose our maximum chunk size is 10,000 bytes, but for whatever reason, we're only testing with an itty-bitty 3-byte message. The obvious fix is to deliberately use a message larger than our maximum chunk size. And with this kind of messaging, that's downright trivial. We just take the maximum size, add some, and make that big a message. But now let's look at another possible cause and solution. Maybe we did test with the largest permissible message out of a set of predefined messages, or at least message sizes. For instance, here we have small and large message sizes, and we test with a large, and yet the mutant has survived. How could that be? On the other claw, what's so bad about that? It sounds like a good thing to me that we're still sending the message in one chunk. But either way, the mutant is probably trying to tell us something. What is it trying to tell us? In this scenario, it's trying to tell us that a version of send message with the looping removed will do the job just fine. If we remove the looping, we wind up with this code, like I showed you earlier. And if we run our mutation testing tool on this, it would show a lot more stuff as just being redundant because it would only be there to support the looping. If we get rid of that other stuff, we wind up with this. And now the message is very clear that send message may well be redundant. Now, in real-world code, maybe it's not, because maybe there's some logging and error handling and whatnot that we need in send message and can't shove down the stack into send bytes. But at the very least, the looping was redundant. Fortunately, when it's this kind of problem with redundant or unreachable or otherwise ineffective code, the solution is clear and easy. Just get rid of it. This will also make our code more maintainable by getting rid of useless cruft that was just getting in the way of understanding it. Now that we've seen a couple scenarios of finding bad tests and redundant code, I'll address some occasionally asked questions. Mutation testing is still rare enough that I don't think there are any really frequently asked questions. First, this whole idea seems really weird. Making tests fail to prove that the code succeeds. Where did this bizarro idea come from in the first place? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 in Richard Lipton's term paper titled False Diagnosis of Computer Programs at Carnegie Mellon University. The first tool didn't even appear until 1980 as part of Timothy Budd's PhD work at Yale. But even then, it was still just not practical on typical developer-grade machines. And this is a 2020 MacBook Air. I could do some decent mutation testing on that, even though those of you who are using a laptop for your development work are probably using something much more powerful than this. It wasn't really practical until about the early 2000s, with significant advances in CPU speed, multi-core CPU, and larger and cheaper memory, and so forth. But that leads us to the next question. Why is it so CPU and memory intensive? To answer that, we need to do a little bit of math, but don't worry, it's pretty basic. I'm not going to ask anyone to divide or subtract. Suppose our functions have, on average, about 10 lines each, and each line has about 5 places where it can be mutated to any of about 20 alternatives. That works out to about 1,000 mutants per function. And for each one, we'll have to run somewhere between one of the function's unit tests, if we get really lucky and kill it on the first try, all the way up to all of that function's tests if we kill it on the last shot, or it, of course, survives and escapes. Suppose we wind up running, on average, just 1/5 of the tests for each mutant. Since we start with 1,000 mutants per function, that's still 200 times as many test runs as just running your test suite. So if our tests normally take a zippy 10 seconds, at least with these assumptions, it'll take somewhere around 2,000 seconds. Now, that might not sound like much because I'm saying seconds, but do the math, and it's over half an hour. I don't know about you, but I don't want to sit and wait for that. We all know the value of tight feedback loops, right? This would totally ruin that. So that's one of the reasons that filtering I spoke of at the start can be so helpful. To summarize at last, mutation testing is a powerful technique to help ensure that our code is meaningful and our tests are strict. It's pretty easy to get started with in terms of things like setting up the tools and maybe annotating our tests if need be. Yes, it may be tedious and time-consuming, but at least it should be easy. But it's not so easy to interpret the results, nor is it easy on the CPU. Even if these drawbacks mean it might not be quite so perfect a fit for our projects right now, I think it's still just a really cool idea in a geeky kind of way. If you'd like to try mutation testing for yourself, here's a list of tools for lots of popular languages and platforms, and some not so popular. I doubt anybody's doing much Fortran 77 these days. Don't bother trying to read all that now. The final slide has the URL for all the slides, including this one. And the tools I know are outdated are crossed out. Not sure how well that's showing up there. Yeah, you can see that. But I don't know or follow quite all of these. And now it's your turn. If you have any questions, I'll take them now. Else there's my contact information and the URL for the slides with a full script, which I've mostly stuck to. So, any questions? Crickets. Okay, question. Mm-hmm. Hmm. Okay, to summarize the question, he tried mutation testing using Striker for C#, I think you said it was? Yes, very popular tool. Striker also supports a number of other languages, and it was loading down the CPU quite a lot. Is there some way to narrow it down and say, okay, only mutate this stuff in this PR? Now, I do not know offhand exactly what sort of filtering Stryker has built in, but it wouldn't surprise me if it has some way to tell it, just mutate this function, this function, this function, maybe this file, if there's like some file with lots of changes all through it. And that would reduce it significantly compared to this function out of this huge file and all those files out of some huge set of directories. I guess you just look at the command line arguments it usually is and see, okay, is there one to narrow it down? And let me know what you find there.